Today our topic will be linear homogeneous PDE with the constant coefficients, right? In the last video we discussed about the Lagrange's form, that is PP plus QQ equal to capital R, and the solution were given by Lagrange's subsidiary equation. In this video too we will be using those Lagrange's subsidiary equation, and as the topic suggests that the equation will be linear. As you already know that what is the linear PDE, when every term has a degree 1 or 0, means every derivative term, if del z over del x or del z over del y is present there, then it should be of degree 1, right? So let me write the definition of linear homogeneous PDE with constant coefficient. So a PDE of the form a naught del nz del xn plus a1 del nz del x n minus 1 del y plus a2 del nz over del x n minus 2 del y2 plus a n del nz over del yn equal to some function. Suppose the function is capital G x comma y, right, where a naught, a1, a2 up to an are constant coefficients, or you must write constants only, okay, and g x comma y is a function of x and y. So looking at this PDE, notice that since each derivative term, the partial derivative, each of the partial derivative, this is the nth order partial derivative with respect to x. Similarly, this is the nth order partial derivative with respect to y. But this is also the nth order partial derivative. This is called mixed derivative because it has been derivated n minus 1 times with respect to x and once with respect to y. Similarly, this is also the nth derivative, nth order partial derivative with respect to x n minus 2 times and with respect to y 2 times. While these two are pure derivatives, this is pure derivative with respect to x and this pure derivative with respect to y. You see that the degree of the each term is 1, means you can see that here we have 1, all the derivatives have degree 1 and so on for all these terms, right? That's why we are calling it a linear, right? This is the property of a linear equation. Every term should be of degree 1, right? And the reason behind writing this word, why we are calling it a homogeneous PDE, homogeneous here means that every derivative is of degree n. See this partial derivative is of order n, this partial derivative is of order n, this is of order n, every derivative, every partial derivative is of order n. That's why we call it homogeneous. And this word is misleading, as you have studied in ODE, ordinary differential equation, in the previous semesters. Homogeneous is used for the PDE if the right hand side is 0 in case of ODE, but that is not the case here. It has homogeneous or non-homogeneous has nothing to do with the right hand side. Make it very clear. Homogeneous means every derivative is of same order, every derivative is of nth order. That's why we are calling it homogeneous. Maybe you may think like that, if a function xy is like this, x square y square plus 2xy cube plus 3x cube y, then we call it homogeneous because every term is of same nature, means same degree, 4 degree, 4 for 4. So this is the idea, to call it homogeneous for this PDE. This is the idea. behind it, why this function is homogeneous. But as soon as I write x, y, this is non-homogeneous due to this term, right? So homogeneous word is used in different sense in case of PDE. Okay. And why we are writing constant coefficients? Because every coefficient, the coefficient of each partial derivative is a constant. A0, A1, A2, they are all constants. Okay. Now, this PDE can be written in much simplified form as if I write del over del x, this is the partial derivative, or you can say it an operator. If I write it here, z can be written here also, then it is represented by the symbol capital D, and del upon del y, this operator is represented by d dash, right? Then this equation can be written as this can be written as a naught, that will be the nth order derivative with respect to x, and del by del x is denoted by capital D, so I should write d to the power n, right? And z is present here, okay, z plus this term a1, and now see this is the mixed derivative, and n minus 1 times with respect to x, that is I have to write d n minus 1, and only once with respect to y, so I have to write d dash, and this is my 1, okay, 1, this is d dash. Similarly for this term a2 d to the power n minus 2, it indicates that n minus 2 times the derivative of x, derivative of z with respect to x, and dy del y square, it indicates that d dash square, right? Plus last term an, since being a pure derivative in y, I have to write d dash to the power n, and since for every term, every derivative is with respect to, is the dependent variable is z, so I have to write z here, z for every term, or should I write z outside this, z equal to this g x comma y. So this can be written in this simplified form, right? And what is d? D is del by del x, and d dash is del by del y. Okay. And now you see that you can write this as an operator. This is an operator. This is not a function. This is an operator operated on the dependent variable g, and we get gxy. You can think like that. Okay. So you can write it as it is an operator containing d as well as d dash, containing various powers of d and various powers of d dash. So it can be simplified to this form also: f d comma d dash z equal to g x comma y, where this whole term in the parenthesis has been replaced by f d comma d dash. Notice that this is a kind of operator, right, containing the derivatives, partial derivatives with respect to x, y, and mixed derivatives also. Or you can think in another way that it is like a function of d and d dash, which when operated on z gives gxy, means a function needs some input and gives some output. You can think like that. This is a kind of function having z as an input and gxy as an output, right? Okay. So now we see that this is an operator in d and d dash. So what is the process to solve this linear PDE? I am writing that since f d comma d dash is always, can be always expressed as the product of linear factors like d minus m1 d dash, the first linear factor, d minus m2 d dash, and so on. Last will be d minus mn d dash, then z is equal to capital F x comma y. Now see that you can factorize this whole term in bracket in the following way, means in as a product of linear factors. And why I am saying so, that because you are allowed to use any m1 m2 mn, maybe a real number or a complex number. Any polynomial is always factorizable as a product of linear factors if you allow yourself that the roots are complex, like this. Suppose you have this equation x square plus 1 equal to 0, right? If you restrict yourself that x is a real number, then it has no solution. You cannot factorize it. But if you allow yourself that x may be a complex number, then you can always factorize this x plus iota, x minus iota equal to 0. So allowing yourself that x belong to complex number, then you can always factorize it in as a product of linear factors, right? That's why we have written that FDD dash can be always expressed as a product of linear factors, because we allow ourselves to have these m1 m2 up to mn as complex numbers, right? Okay. And now you see that we have two cases after this equation. Let me call it equation number A, equation number capital A, right? We have two cases. One case is where fxy is equal to 0. That is the simplest case. And another case maybe in our next video lectures when fxy is non-zero. So I'm starting with fxy is equal to 0, the simplest case. Case 1, that is if this is not f, sorry, this is capital G. If capital G x comma y is equal to 0. So my equation A will be reduced to, then equation number A becomes d minus m1 d dash and d minus m2 d dash up to d minus mn d dash z is equal to 0. Now we are going to solve this PDE particularly when the right hand side is 0. And notice that how many factors are there? 1, 2 up to n factors. And why I have written n factors? Because see this, the degree of this equation is n. Degree in the sense, if you take it as a polynomial, means if you think like that, this is a variable x, a naught x to the power n, then we can say that degree is n. Otherwise, it is not degree. Or n is the order of the differential equation. But I am saying it as a degree because I am going to factorize it, and to factorize it, I have to think in that way that it is like a x or m, right? Okay, so that's why I've written n factors. Okay, now here comes the theory of our last video, Lagrange's form, where starting with any of these means z can be taken here. Okay, so starting with any of these factors, or should I write the solution directly? Then I will explain it. We have two cases. Two cases arise, right? Now this is case number 1. After this, first case is if m1 is not equal to m2 is not equal to m3 is not equal to up to the last root mn, means this is already in factorized form, and if you put every factor is equal to 0, then m1 m2 m3 equal to not equal to, sorry, these roots will be obtained, right? If this is the case, then the solution is given by z equal to, right? Why I'm writing z? Because z is the dependent variable. Z has to appear on the left hand side. Z is equal to f1 y plus m1x plus f2 y plus m2x plus up to fn, obviously y plus mn x. So in that case, this will be the solution, and I will explain that why is the solution, why this is a solution, explanation behind this or reason behind this. And the reason comes from the Lagrange's PDE, means taking one factor once. Suppose I take this factor, or in general, like I should write d minus md dash. Particularly, I am writing particularly for only one factor. Particularly, if d minus m, I am writing it as m1, m2 in place of these suffixes. I am just writing m. D dash z equal to 0 for any of these factors equal to 0. Okay. Should I multiply this? Oh no, not multiply. Should I operate? This is not multiplication. This is operator operated on this z, or you can say that function with this input, right? So do not use the word multiply. D operated on z and d dash operated on z. This will become d z minus m d dash z equal to 0. And what is the dz? D is actually del over del x, right? And then it becomes del z over del x, and then it becomes small p minus m d dash z, that is del z over del y, and this is over small q equal to 0, right? And you now see this equation. This is similar to the last Lagrange's form, pp plus qq equal to r. It is Lagrange's form. Lagrange's form of PDE, the first order first degree PDE. So we are Lagrange's subsidiary equations. Subsidiary equations are given by dx over capital P, which is 1 here, and dy over capital Q, which is minus m, and dz over 0, right? And then we take any two ratios at a time. Suppose I take first two ratios, then I will get taking dx over 1 equal to dy over minus m. I am simplifying and integrating. I will get gives, I'm writing it directly, that will be x y y plus mx, y plus mx equal to c1, and c1 is a constant of integration. That is my first relation, right? And similarly, taking any two ratios, means third ratio combined with second ratio, then ultimately the 0 gets multiplied here, then I will get dz equal to 0. Remember the case when the 0 appears in the denominator over some dx, dy over dz. So in that case, dz over 0 equal to any ratio, take any ratio gives dz equal to 0, because 0 gets multiplied here, and dz equal to 0 means on integration I will get z equal to c2, right? And to understand these calculations in detail, please refer to our last video, that is on this form, pp plus qq equal to r. Okay, so combining these two, on combination of these two on combining gives me the solution, gives z is equal to f of y plus mx, and notice that z equal to c2, or should I write it in more, gives, first it gives phi z comma y plus mx equal to 0, and after writing this way I can write that z is equal to f of this thing, or z equal to f y plus mx, right? So the solution is of form z equal to f y plus mx, and that's why, see here, the first solution corresponding to m1 root, f1 equal to y plus m1x. Corresponding to this one, I will get this. Corresponding to this one, I will get this. And notice that why we have added these all solutions, why we have added them, because as you know that for any linear differential equation, whether it is an ODE or it is a PDE, if y1, y2, y3, y up to yn are linearly independent solutions, then they can always be added up to give the full solution, as you remember from the theory of ODE, right? So this is just the linear combination of all solutions, first solution, second solution, and so on, and then you add them to get the full solution. This is why we call it linear PDE. This is a basic characteristic of linear differential equation, whether it is ordinary or it is partial differential equation. Okay, so this was my one of the cases out of two cases. Now I am going to discuss the second case, when some of the roots m1, m2, m3 and so on, they may be equal, right? Okay, I don't need this equation. This gxy becomes 0 in our case. I need that equation only. Equation number A is reduced to equation number B. I will write it as equation number B. I need this equation. Okay, now the first case, now second case second. And if some of the roots are equal, if suppose m1 is equal to m2 is further equal to dash dash is equal to mk, some of the roots are equal, and after that mk means mk, there mk plus 1 not equal to mk plus 2 not equal to dash 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 or not equal to mn, right? So out of total n roots, we have k roots equal, and after k roots, all roots are distinct, and obviously k should be less than n. That is obvious. Okay, so in that case, then the solution is given by z equal to f1 y plus m1x plus x times f2 y plus m2x, and see this x times, this x has been introduced here, and then x square times f3 y plus m3x, and up to that will be x to the power k, because k roots are equal, then x to the power k. So it should be x to the power k, x to the power k minus 1. If two roots are equal, then I have these two terms. Okay, then x to the power k minus 1, I think 1 less f, obviously k, because here we have f2 and the power is 2 minus 1. So, and here we have f3 and the power is 3 minus 1. So the exponent of x should be 1 lesser than this suffix. Notice that. Okay, fk of y plus mk x, and after that you have all distinct roots, then you write fk plus 1 y plus m k plus 1 x up to the last fn y plus mn x. So that is the solution in case number 2, when some of the roots are equal. Okay, and let me write the reason why I have written the reason for this, why we have put x and then x square. Okay, reason. So in particular, we can say that if only two roots are equal, only two roots, okay, then the solution will be of the form f1 y plus m1x plus x times f2 y plus m2x, and after that the solution will be written for these distinct roots. So we are particularly focusing on a small case when two of the roots are equal, and I will try to prove why this x appears here, right? Okay, so reason, I'm writing the reason. In particular, if I choose k is equal to 2, what does it mean? Means only two roots are equal, m1 equal to m2, that's it. Means two roots are equal, that is two roots are equal. Okay, fine, right? In that case, what will happen if two m1 equal to m2 happens, then obviously the first two linear factors will be same, d minus m1 d dash and d minus m1 d dash, and after that all factors will be distinct. right? We are discussing the case when only two factors are same. You can say that from this, when only two factors are similar, right, containing the same m. Okay, if k equal to 2, then d minus md dash into d minus md dash again, or should I write it as 2 square anything z equal to 0. So this will be a factor present in our equation number b, right? If we want equal roots, some of the roots are equal, then obviously this factor will be present here, maybe at the beginning. Okay, now you may write it as d minus md dash, again d minus md dash z equal to 0. Okay, let me take this term as a small v, right? Let d minus md dash operated on z gives a new function, let it be small v, right? Think in that way, when this operator operates on z, gives something, you cannot say that this immediately gives 0, because when d minus md dash is operated on this thing, then it gives 0. So you cannot say that directly it gives 0 at the first place, right? You have to assume that it is some v. V may be or may not be 0. Okay, then d minus d md dash z equal to v, and putting this here I will get, then d, I'm writing it as equation number suppose 1, then first becomes, then equation 1 becomes d minus md dash v equal to 0. Let me just say, okay, then my equation number 1 becomes this. Now I am going to solve this equation number 2. Solving equation number 2. On solving equation number 2, which is again of the same form as the Lagrange's form, see this, d minus md dash z, in place of z I have v, right? So obviously the solution will be similar to this, and the solution will be v equal to f of y plus mx, right? Z is replaced by v because the dependent variable this time is small v, so I'm not doing that. I will just write the solution directly. Okay, on solving I get v equal to f y plus mx, right, as a solution of this equation number 2. Okay, now I've got the value of v. Okay, right, or should I write it as at least these two values, y plus mx is equal to c1. I should write them, or I should write it as where y plus mx must be equal to some constant, let the constant be c1. I have to mention this thing, what is my y plus mx, that is equal to some constant, right? So y plus mx is equal to c1, right? Then my equation, which equation? Yes, equation number 1 or this, you can say this one. Then equation 1 becomes d minus md dash, then operated on this thing, but this is a small v. No, we again move to equation number 2. No, that is wrong. I found v in terms of this. If I put v equal to this thing, I have solved equation number 2. I should solve this. Let it be equation number 2, and this is 3, and on solving 3 I should put on equation number 2, then equation 2, right, d minus md dash z equal to my small v, and what is my small v? F of y plus mx, but remember y plus mx is equal to c1, remember that. Okay, now again this is Lagrange's form PD, but see this time the right hand side is fc1. Okay, and if I solve this, I have to solve this again, this is Lagrange's form. Okay, so writing the auxiliary Lagrange's subsidiary equation, Lagrange's subsidiary equations, I will get dx over the coefficient of small p, that will be 1, and dy over minus m, and dz, this time the third variable, dependent variable is z, dz over f of c1. Okay, right. This was my first case. Okay. Then on solving, taking first two ratios and taking the other ratios, let me take the first two ratios. Taking first two ratios, that is dx over 1 equal to dy over minus m, we get what we get, cross multiply, integrate, I will get y plus mx equal to some constant, and this time the constant let it be c2, right? Okay, and taking the first ratio equal to third ratio, dz over f of c1, and on integration it will give, I think fc1 gets multiplied here, then it will give we get it, integration will be z equal to x of times fc1, because integration of dx will be x, right? And now from these two gives the solution in this form phi, and within bracket we have z, no, not z, z by x, z upon x, or z upon x. And there is a new constant. If I integrate this, then I will have some new constant also. I think x c1 plus c2, and let me write it here, z minus c2, or z minus x f c1 equal to c2, right? Integration twice, we will get two constants, c2, and this will be, sorry, c3, new constant, c2, c3. Now this is fine. Okay, now see that combining these two this way and then finally writing this way means z is equal to some constant, and then constant equal to function of some y or x. Similarly, I am writing it directly here, not writing in terms of phi, gives z minus x f c1 equal to some function of y plus mx, and this x fc1 goes here, or it becomes z equal to f of y plus mx plus x times of fc1. And remember what was my c1? See, this was my c1. What is that? c1. Oh, c1. Where is the c1? This is my c1. c1 is equal to y plus mx. We have mentioned it here. c1 equal to y plus mx, right? Then I will get f plus x times f y plus mx, right? And see this y, we have got the reason why we have x at this position, right? This is the explanation for this x. Similarly, if I take 3 roots equal to k equal to 3, then I will get something like that, z equal to fy plus mx plus x times fy plus mx plus x square times fy plus mx. So this is the reason for the presence of this x here. Okay, now we have only two cases, because we don't have this time as a classification in form of real roots or complex roots. The roots may be you are free, means you have an open domain of complex roots. Roots may be complex, so whether they are distinct, whether they are same, we have only two cases, right? So we have to remember this formula. Like once this formula for distinct roots, where is that? This is the formula for distinct roots. This will go with us in the numericals. Distinct roots, or I should say distinct factors, and this is the formula for some of the repeated roots. Some are all repeated roots, right? This will go in numericals. Okay. Okay. Suppose I take example d square minus 5 d dash plus 6 d dash square z equal to 0. Okay. Then since this is the second order homogeneous linear PDE, so starting from the same theory, trying to factorize it, I can write it as d square minus 5 d dash plus 6 d dash square z equal to 0, right? And this is very similar to a quadratic equation. The 6, we need 6, two numbers whose product is 6 and sum is minus 5. So I will write it as d square minus 3 d dash minus 2 d dash, and taking common and doing simplification, I will get something like this: 2 minus d minus 2 d dash and d minus 3 d dash z equal to 0. Now comparing this result with this one, the factorized form d minus m1 d dash d minus m2 d dash, the previous statement, then I will get the solution like this form: f1 y plus m1x plus f2 y plus m2x, and so on, because 2 and 3 are distinct roots. Therefore solution will be of form z is equal to, note that z is a dependent variable, so on left hand side you should write z, f1 y plus 2x, right, and plus f2 y plus 3x is the solution. Notice that the sign of this root gets reversed here. If this is minus, then here it will become plus, or plus becomes minus. And one more thing I want to add here, that note, in some books or some authors tend to write this PDE in this form. They put d equal to m and d dash equal to 1. This is another method to factorize this equation, and in that case they write m square minus 5 m plus 6 equal to 0. Putting d equal to m and d dash equal to 1 will give this kind of equation, quadratic equation in M, and it appears that the factorizing this equation is very easy as compared to this, because here we get mess up with all these d and d dash. For a student this looks quite good, but what happens in this case, m minus 2 m minus 3 equal to 0, that is fine, and I get m is equal to 2 and m is equal to 3, again this is fine, and we see that the roots are distinct. So applying that formula, again the solution z is equal to f1 y plus 2x plus f2 y plus 3x is the solution, and this is indeed the same as I obtained by this method. But this method looks good, but it has some demerits also, and we'll see in our later examples that what are the demerits of this question, demerits for this method. Okay, now example number 2. Example number 2, let me take an equation like d square minus 4 d dash plus 4 d dash square z equal to 0. Okay, d dash. Then I will follow this method. It looks good, but it has some demerits. Okay, so I am following to the first method. The factorized form will be d minus 2 d dash whole square. It is clear, or you can write it twice: d minus 2 d dash z equal to 0. Right. In this case, I am getting two equal values of m, 2 and 2, and I have to use that case number 2. Case 2 was when we get equal factors or repeated factors. We had the solution in this form: z is equal to f1 y plus 2x, and again we write this thing, but this time x multiplied by f2 y plus 2x. This will be the solution, and you know the reason why this x appears here. Okay, so example number 3. Suppose this is a cubic equation and I got 3 roots which are equal to 2, 2, 2. right? In that case, I will write f1 y plus 2x, x times f2 y plus 2x, and x square times f3 y plus 2x. Means the multiplicity of x will be repeated accordingly, or it can be increased accordingly. Example number 3. Let me take another example for which let me take that example which contradicts this method. This one particularly. Okay. The example is d square or d cube d dash square minus d square d dash cube operated on z is equal to 0. I will put a star on this example. And why I am putting a star? Because this question is contradicting this method, writing d equal to m and d dash equal to 1. If you follow this method, which looks good to a student, then what happens here? If you put d equal to m and d dash equal to 1, then you will get something like this: m cube minus m square equal to 0. And this is the danger point. Why? You see that the order of the differential equation is 5. 3 plus 2 is 5, and you have got a third degree equation, and that is, you are going to get 3 roots only, maybe 1, 2, 3 roots. First root will be 0 and 0, another root will be 1. Only 3 roots are here, but the order was 5. It indicates that by this method you just missed 2 roots, and that's why this method is avoided. Means this is not 100% correct. So sticking to our original method, factorizing in the d and d dash. Look what happens. Try to take common. What is common in these two terms? D square d dash square, and inside bracket d minus d dash z equal to 0. Remember that you have to factorize each and every term as a linear factor. This is linear factor, this is not linear, d square and d dash square. So writing in linear factors, I should write it as, first is d square, and see what happens when I write in form of factor, and the factor is the form d minus m d dash. I should write it as d minus m is absent, 0 d dash square. This is for this term, d square. This term is written in this way, and this term d dash square should be written this way. So d is absent here, 0 d minus 1 d dash square. Is it clear? Right. And the next term will be, next factor will be d minus d dash z equal to 0. So ultimately I have got all terms as a product of linear factors. Okay. The solution will be z equal to, or try to write the solution for this term. I will have y, and this sign gets reversed, as you see here. Minus sign will become plus, and in place of d, y gets in, and 2d dash becomes 2x. So this should be z equal to f1 y, and this minus becomes plus 0, and d dash becomes x. And what about this square? For square, see this, if a factor is present twice, then we have to put an x factor here. That will become x times this solution. f2, remember the subscript will be changed, f1 f2, y plus 0 x, and this is the solution for this first two factors. Writing solution for this one, I will have 0y plus x, f3 0y plus x, and since it is repeated twice, so I will put x before this solution, f4 0y plus x. Okay, now only the remaining factor is d minus d dash, and this is very easy. I have to write f5 y plus x. So this is the complete solution, and you see that writing d equal to m and d dash equal to 1 will work 99%, but in 1% examples it will fail. So you have to be on your own guard to use this method. Be careful, this method is applicable if and only if you don't lose the degree, you don't lose the power. Like in this case, you can use this method. This looks good, and factorization is very easy. but be careful. You, or I should write it as, this method is useful. If I put a small remark here, if and only if you have the first coefficient, means a naught is not equal to 0. And remember, what was our a naught? A naught was the coefficient of the pure nth order derivative of the first term, and if that is not 0, then you can use this method. If a naught equal to 0, then this method completely fails. Okay, taking another example, maybe kind of example which has repeated roots and distinct roots as well. Example number 4, and let me write it as d cube minus 3 d square d dash plus 3 d dash square minus 1, and then operated on z equal to 0. Okay, sorry, this should be d dash cube, because it is homogeneous equation. Every term should be of degree 1 and order 4, right? Order 3. Okay, the solution is given by writing. You can use this method this time, because see that the highest derivative, that is the pure derivative in x, and this coefficient is 1, this is not 0. Had it be 0, then I cannot use this method. So luckily we can use this method. In order to factorize it, we will be getting a cubic equation, and solving a cubic equation in d and d dash will be messy. So auxiliary equation, we write it auxiliary equation or characteristic equation. Auxiliary equation, this time I am using this method. D equal to m and d dash equal to 1. D equal to m and d dash equal to 1. I get m cube minus 3m square plus 3m minus 1 equal to 0. And I'll put a star on this step. Notice this step. See the degree of the equation, m cube, and the original PDE was also of order 3. That's why this method is preferred in this example. Okay, let me try to factorize it. There are many ways to factorize it. A student may find that this is actually the cube formula. If I write m minus 1 whole cube, m cube minus 1 minus 3m square plus 3m, it may be the case that a student find that it is a cubic cube formula, or you may not find that it is a cube formula. Then you have to use your tricks to find the root of equation, or use the theory of equation. Then how to find its root? By trial, because it's a cubic equation, it cannot be solved directly as in case of quadratic equation. So you have to make a guess to at least find its first root, and to guess about its root, the perfect guess would be plus minus 1. And why it is plus minus 1? I mean, take or put m equal to 1, and the point behind putting m equal to 1, why not m equal to 0, or why not m equal to 2? Because that guess will work, that number should divide this constant, and see this constant, this is plus minus 1, right? And minus 1 is divisible by plus 1 or minus 1. So the root may be 1 or minus 1. 2, 3, 4, 5, 6, they cannot be the roots of this equation, because the root always divides the constant term. Okay, so making a guess with m equal to 1, you put 1 here, and you will get 1 minus 3 plus 3 and minus 1. Then ultimately we will get 0, means m equal to 1 is the one of the root of the equation. Or I should write it as, let me call it some function fm. Let fm, I'm calling it fm, function of m cube minus 3m square plus 3m minus 1. And by hit and trial, but calculated trial, by trial, you see that f1 equal to 0, because 1 is the root of the equation. And why 1 is, when 1 may be the root, by the, that is called rational root test. Rational root test says that an equation may have a root alpha if and only if the alpha divides the constant term. That's called the rational root test, and I have used that test to find the first root of this equation, that is f1. And luckily I see that If I put 1 here, I am getting 0, right? And now my another guess should be -1, because -1 also divides this constant. So putting -1 here, I will get -1, and this will be -3, this will be -3, and -1, ultimately I will get -8. So -1 is not the root, right? So 1 is the only root. And to find other two roots, there are two methods. Either you divide this polynomial by m-1, that is called remainder theorem, you use in class 6th or 7th, or you can use some another facts that there may be a case that 1 is a double or triple root of this equation, and how to find that 1 is the double root or triple root. Double means a root appearing twice, so triple means root appearing thrice. You have to do some derivatives, means differentiate this function in your mind. What is f dash of m? F dash of m will be, I'm writing it here, what is f dash of m? We see that f dash m, what is f dash m? 3m square minus 6m plus 3, right? Let me calculate f double dash m also. F double dash m is equal to 6m minus 6, and f triple dash, that will be constant 6. Now writing these derivatives in your mind, or just write it, then you see that if I put 1 here, then I get f1 equal to 0, means 1 is the root of this equation, that is sure. But if I put 1 here in f dash m, I am getting 0. See, 3 minus 6 plus 3 equal to 0. And if I put m equal to 1 in the double derivative, again I am getting 0. 6 into 1 minus 6 equal to 0. But this is a constant, means up to second derivative, the function is 0. What does it mean actually? We see that f dash equal to m, and f dash 1 equal to 0, and f double dash 1 is also equal to 0, and this is not equal to 0 in any case. F triple dash 1 is not equal to 0. So what does it mean? We see that f1 equal to 0, f dash 1 equal to 0, f double dash 1 equal to 0. It indicates that 1 is the root of this equation with multiplicity 3, means 1 is the only root of this equation, 1, 1 and 1, and that's it, we are done, right? Since f1 equal to f dash 1 equal to f double dash 1 equal to 0, and we see that this triple derivative is not equal to 0, it indicates that therefore 1 is the only root, or we can say that m is equal to 1, 1, 1, root with multiplicity 3. So this derivative test may be useful in order to avoid the division algorithm. Okay. Now getting its root for thrice, the solution will be of form z is equal to f1 y plus x plus, since the root is repeated, I have to put a x here, x times f2 y plus x plus x square times, increase the multiplicity of x in each factor, x square times f3 y plus x, and this is the solution of this equation. And see how many arbitrary functions are there, 1, 2 and 3, and indeed the order of the equation was 3, means 3 order equation has 3 arbitrary functions, right? And I think the examples we have done are sufficient to understand how to solve a homogeneous linear PDE for the case when the right hand side is 0, and in our next videos we will be seeing the case when the right hand side, that is gxy, is not equal to 0. And that's it for this video. Thank you.